Welcome to the second part of Minilecture 4. We were talking about how, in an asymptotic giant branch star, gravity is trying to squeeze carbon and oxygen down to begin nuclear fusion.
So before gravity can squeeze the carbon and oxygen enough to make it hot enough to begin fusion, a new type of gas pressure appears. We call this degeneracy pressure, and one way of thinking of it is basically that if you have a bunch of electrons flying around in this core of the sun, and there comes a point where if you squeeze it any further, you're going to try and put two electrons in the same place at the same time. The electrons don't want to do that. They don't want to overlap. They don't want to rub shoulders. So they fight against it. They press outward, and they're able to stop gravity. So the gravitational shrinking of the core of the sun stops at this point. So here's our typical degenerate explaining to us why it doesn't want to be squeezed anymore. It's done enough work. And basically what you end up with, whereas in a normal gas atoms are flying all around, in a degenerate state they're packed so tight together that while it's still a gas, you can't press them any closer. This will stop gravitational contraction. This degenerate core of the sun, carbon and oxygen, it will contain half of the sun's total mass, half the sun's current mass, but it's going to be squeezed by gravity into something about the size of the Earth. Meanwhile, the remaining half of the sun is in this red giant that reaches out to beyond the orbit of the Earth. So half the sun's mass is in this little tiny white dot. You may not even be able to see it after this video has been rendered. This is not a stable situation. Once the star reaches this point, the outer layers of the star are barely being held on by gravity to the surface of the star, and this degenerate core, this carbon and oxygen lump at the center of the star, a wind appears at the edges of this lump that pushes the outer layers of the star out into space. So the outer half of the star kind of floats off in a gentle breeze, moving outward away from the star, never to come back. The inner part is this lump the size of the Earth that's been squeezed so tight, it's really tightly held together. This lump of carbon and oxygen ash that's been squeezed so tight is extraordinarily hot. It's been doing nuclear fusion at a temperature of over 100 million degrees. So its black body radiation is peaking in the X-rays and the ultraviolet. This is enough energy to light up the rest of the gas that's now moving outwards, and as it moves outwards it's thinning out. So we have a thin, cool gas being energized by a very hot energetic source, and so it begins to glow as an emission nebula. This is the planetary nebula phase, the planetary nebulae that we talked about in the first mini lecture. Here a picture of a couple of planetary nebulae. You see for the most part they're round. The colors here are emphasized. They're not necessarily natural colors. But what you notice is that in the star on the left, the Cat's Eye Nebula, you can see this nuclear core, this hot, dense star, at the center of these thin shells of gas around it. In the star on the right, there's actually some dust that's blocking our view of the hot, dense former nuclear reactor of the star. But again, you can see these delicate tendrils coming off into space. Here are a couple more planetary nebulae. The one on the upper left is called the Eskimo Nebula. In this picture you can see kind of why. It looks like he's got a big furry parka around a head. Again, notice there's a dot right at the center. That is the former nuclear reactor of the star that made this nebula, glowing very hot, hot enough to energize the whole thing. In the lower right, we have one last planetary nebula, where again you see the bright star at the center. Here you notice though that we don't have a round shape, we have an hourglass shape. In this case the gas isn't coming off nicely all the way around the star, but it's blowing off at the poles of the star, and that's what makes a shape like this. A planetary nebula doesn't last very long, at least not in astronomical terms. It only lasts a few tens of thousands of years, if that, maybe just 10,000 years. And then the gas that used to be on the star drifts far enough into space that it cools off, it becomes transparent, and it rejoins the interstellar medium where it can be recycled into more stars. However, that former nuclear reactor stays behind. This core of carbon and oxygen ash, it starts off really hot, but it has no energy source, can't do any fusion, so it's going to cool off over time as it loses energy. And as it cools off, it'll become fainter, and it'll become redder in color. But it starts off white hot, but it's really faint because it's so small. Remember, this is only the size of the Earth. So we call this a white dwarf. Here's a picture taken by the Hubble telescope of the star Sirius. And if you remember when we did the night sky, we learned that Sirius is really a binary star. The bright star that we can see with our eye is called Sirius A, and it has a white dwarf companion, Sirius B. Sirius B is this little tiny dot below and to the left of Sirius A, and it's a star that lived out its life and has now died. It's gone through the planetary nebula. All the planetary nebula has gone off into space and cooled off, and what we see is a white dwarf. Now if we magnify this to get closer and see what a white dwarf actually looks like, it looks something, oh gosh, I think our artist was on something again. That is a white dwarf, but it's not a star. So let's go to a different artist. This is better. So something white hot, half the mass of the sun, squeezed into something a little bigger than the Earth. This is a very extreme object. If you imagine squeezing half of the sun into something the size of the Earth, gravity gets really strong. If you weigh 100 pounds on the Earth, on the surface of a white dwarf, you would weigh 100,000 times that, or roughly 10 million pounds. You'd be squished into a little grease puddle before you could say Jack Robinson. Another way is imagining that you've taken an elephant and squeezed it into a thimble. That's roughly the density of this material. So here's a summary of a low-mass star's life. Now your book uses this weird numbering scheme. I've never seen this numbering scheme anywhere else. No one talks about stage 2 of a star's life or stage 5 of a star's life, but I've used those numbers here just to be consistent with your book. After a star forms, it's on the main sequence. That's stage 7 here. So this is a sun-like star. It'll stay there until it uses up all the hydrogen in its core by nuclear fusion. Gravity will then squeeze that helium that's been formed, and in doing so it makes the core of the star denser, the outer part of the star fluffs out, and we get a red giant. The star gets brighter and cooler, up through number 9 on this Hertzsprung-Russell diagram. Now, once it gets to a large red giant, gravity can finally squeeze the core enough that helium fusion can begin, and the helium begins to form carbon and oxygen. At this point, the star shrinks a little bit, gets a little bit hotter, but it very quickly runs out of helium, and so again we have a core of carbon and oxygen ash, a core of ash that cannot do fusion. The gravity is trying to shrink it down, so again the core shrinks, the star expands, it cools off, it gets larger, becomes a red giant a second time. That's number 11 in your thing here. But now gravity cannot squeeze the carbon and oxygen enough to begin fusion, at least not in a low mass star. And so the core gets squeezed as tight as it can into a lump of carbon and oxygen about the size of the Earth. The outer parts of the stars begin to drift off into space and make what's called a planetary nebula. Eventually those outer layers drift far enough off that they cool off and disappear, become transparent again. But that carbon-oxygen core is left behind. That's what we call a white dwarf, because it's hot, but it's very small in radius. Because the white dwarf cannot do any nuclear fusion, over time it will get cooler, but it stays the same size, so it gets cooler and it'll get fainter, and slowly get redder and eventually fade completely away. In our last mini lecture for this unit, we'll go over the life cycle of a high mass star. And what we're going to find is that a high mass star, a star many times the mass of the Sun, has some similarities to the life cycle of a low mass star, but there are some dramatic differences at the very end of a high mass star's life.